The process of forming a black hole is called gravitational collapse, and is characterized by the star becoming denser and denser and its gravitational field becoming more and more concentrated, until the gravity becomes so strong and collapses the mass into a singularity, an infinitesimally small point particle of nearly infinite density. Outside of this point is the event horizon, or the boundary of a black hole, is the line after which nothing can escape the gravitational pull of a black hole. And just outside the event horizon, we have the accretion disk. Any star that is at least 8 solar masses has a chance of becoming a black hole when it dies and collapses, depending on the circumstance. Not all massive or supermassive stars will necessarily become black holes when they collapse at the end of their lives. Billions of years from now, when our star collapses, it has no chance of becoming a black hole. Not that it would matter, because by that point, the expansion of the sun when it becomes a red dwarf would have already eaten the Earth in about 7.6 billion years from now. If a star's collapse does lead to it becoming a black hole, that transition can happen in under a second or a few seconds. Yes, black holes, oddly enough, can be formed in mere seconds. So even if a collapsing star doesn't become a black hole right away at the end of its life, when it collapses, it can still become a black hole through absorbing more material from its nearby space. So say if a collapsed neutron star is able to continually pull in more material from nearby nebulas, gas clouds, or asteroid fields, over millions of years, it can potentially reach the necessary mass and density for the collapse to continue, further becoming a black hole. Another possibility is a neutron star or a collapsed neutron star merging with another star. So say if 2 neutron stars enter each other's orbit and eventually collide, that reaction might lead to a collapse such that it generates a black hole. So either through merging with another star or accretion and accumulating mass from its nearby galactic vicinity, either way this process can take millions of years. Once that collapse starts, it can be as quick as a matter of seconds before gravitational forces pull all the mass of the star down into a singularity. These merges or collapses are extremely powerful and violent. First gravitational wave observed on Earth by LIGO, Laser Interferometry Gravitational Wave Observatories, was due to the merger or the violent crash of 2 neutron stars merging into one, and that created massive ripples of gravitational waves that was detected, and this led to them winning the Nobel Prize in Physics in 2017. In principle, no form of radiation, including radio waves, can escape the event horizon of a black hole. However, black holes can still generate electromagnetic radiation in its vicinity, approaching but not crossing the event horizon. This area is called the accretion disk. The radiation in the accretion disk is generated by the intense gravitational forces and high energy particles in the vicinity, or that are present near the black hole. This radiation can be detected by different telescopes that are sensitive to different types of radiation: gamma rays, radio, X-rays. This radiation can be picked up by land-based telescopes like large radar arrays, or space-based telescopes like the Hubble telescope or the recently launched James Webb Space Telescope. In the accretion disk, material is pulled in closer and closer under the intense gravity of the black hole, and this produces a hot disk of gas around it. This hot disk of gas can then generate X-ray and radio waves that we can study. So imagine a black hole gradually pulling in material from a nearby nebula or gas cloud, and that material will start orbiting the black hole, getting closer and closer, hotter and hotter, and then consequently generating more and more radio waves and X-rays that then our instrumentation and telescopes can pick up. Black holes can be divided up into different categories based on how they're created and their size. First, we have the smallest current size, which is a stellar black hole. A stellar black hole is a black hole that generated from the collapse of a star. They have masses in the tens of solar masses and can be as small as a few kilometers or miles across, so a walking distance black hole. Next up, we have supermassive black holes. Supermassive black holes have masses in the millions, if not billions, of solar masses, and are as large as our solar system. So we're talking about tens to hundreds of astronomical units across. And they are often thought to reside towards the center or the middle of a galaxy, including our very own Milky Way galaxy with Sagittarius A. Third, we have intermediate sized black holes. These are a little bit harder to study and are not as well documented because 1, they're not as common as stellar black holes, and 2, they're not as brilliant or as easy to detect as a supermassive black hole. Intermediate-sized black holes will have a mass of hundreds to thousands of solar masses. A primordial black hole is a type of black hole that is theorized to have existed at the very beginning of the universe in the moments after the Big Bang. After the Big Bang, the universe has all the same mass and energy in the universe right now, but in a much smaller area. At this point, dark energy and expansion of the universe haven't had the time to do their thing and grow space-time. So it was a time of very high density energy and mass. In this early primordial soup of the universe, it's hypothesized that micro black holes could have been generated. So we're talking about the possible existence 14 billion years ago of black holes that were as small as an atom or the size of a hill or a mountain. The existence in the early universe of the primordial black hole is still being debated and has not been experimentally verified yet. So hopefully more advanced instrumentation and telescopes, such as the previously mentioned James Webb Space Telescope, that can peer further back into the earlier universe might be able to give us hints about these early black holes. Another way that we can get data or information from a black hole is through Hawking's radiation. It is a theoretical form of radiation hypothesized to be emitted from black holes, first put forth by the late Stephen Hawking in 1974. The theory of Hawking's radiation came after a 1973 visit to Moscow on behalf of Stephen Hawking. There, Soviet scientists Yakov Zeldovich and Alexei Starobinsky convinced him that a rotating black hole should in some way be emitting particles or energy. Stephen Hawking argued that black holes won't be perfectly black and will still radiate some form of radiation. According to Hawking's theory, black holes should emit radiation because they have a temperature and a corresponding entropy, and due to a relativistic quantum effect. So it's a type of radiation different than the electromagnetic radiation formed by the accretion disk. The event horizon has an energy associated with it because it is the boundary between the inside and the outside of the black hole, and the information of what is inside the black hole is encoded in the event horizon itself. Hawking's radiation is predicted to be extremely weak and has not been measured experimentally yet. However, the theory of Hawking's radiation is still very impactful because it provides a theory to explain black hole evaporation. Hawking's radiation will reduce the mass and the energy of a black hole, and therefore lead to a black hole evaporating over time. Talking about black holes, the nearest one to us will be Sagittarius A, which is towards the center of the Milky Way galaxy. It was first detected as a radio source located at the center of the Milky Way galaxy. It is a supermassive black hole with a mass that is estimated to be about 4 million times that of the Sun. Sagittarius A was first detected in 1970 by radio astronomers that were studying the radio waves emitted from the center of the Milky Way galaxy. It is the most intense and persistent form of radio waves in the galaxy, and is thought to be produced by the high gravitational energy interactions in the accretion disk of Sagittarius A. Sagittarius A is located about 26,000 light years from Earth and is not visible to the naked eye. However, it can be studied by instruments sensitive to radio waves, such as the Very Large Array VLA in New Mexico. The Milky Way is a barred spiral galaxy with a central bar and a number of spiral arms that contain stars, gas, and dust. Sagittarius A is located at the center of the galaxy, near the end of the central bar. However, the galaxy as a whole does not orbit around Sagittarius A the way that the Earth orbits around the Sun. The mass of the Milky Way galaxy is estimated to be about 1 trillion solar masses, while the mass of Sagittarius A is only estimated to be about 4 million solar masses. A quasar, short for a quasi-stellar radio source, is an extremely luminous and energetic object that is located at the center of a galaxy. Their energy output is 1,000 times greater than that of the galaxy itself. Its extreme brightness is how astronomers can detect them at such great distances. Quasars are supermassive black holes with an incredibly energetic accretion disk around it. The accretion disk for a quasar are believed to be far hotter and denser than the accretion disk of most other black holes, or supermassive black holes.